You've probably heard that the universe is getting bigger at a faster rate than scientists expected, thanks to something mysterious called dark energy. But what if this idea isn't quite right? A physicist named Lombriser is challenging our long-held beliefs, suggesting that the universe isn't actually moving away from us. Instead, he argues that it is flat, still, and unchanged. What could back up such a bold claim? Could it be that science has completely misunderstood a basic idea about the universe? Stick around as we dive into this exciting new theory. History shows us that our understanding of the universe has often changed dramatically. Just a century ago, even great minds like Einstein believed that the universe was eternal and unchanging. Back then, many researchers believed that the Milky Way was the sole galaxy in existence. But then, Edwin Hubble came along. While investigating unfamiliar spiral-shaped clouds in the night sky, he made a revolutionary finding. Those nebulae were not part of our galaxy. They were entire galaxies on their own. That single insight dramatically reshaped our cosmic understanding. And it may not be the final occasion we need to reconsider our views. After Hubble broadened our knowledge of the universe almost instantly, he delved even further, calculating the redshifts of far-off galaxies and categorizing them based on distance, size, shape, and brightness. That's when he made a remarkable discovery. The farther a galaxy is from us, the larger its redshift becomes. In simpler terms, the more distant a galaxy is, the quicker it seems to be moving away from us. This consistent trend led Hubble to establish a definitive correlation between redshift and distance, a principle now referred to as the Hubble constant. With this, he became the first to validate what is now considered a cornerstone of astronomy. This finding not only changed textbooks, but also provided insight into the very inception of the universe. If everything is moving outward, then reversing time points us to a singular, dense, and unimaginably small origin. That origin is known as the singularity, the point of origin for space, time, and matter during the Big Bang. For many years, this model of the universe's development appeared to be robust. We had a beginning, an expansion, and even mathematical support for it. But then, the universe surprised us once again. In the 1990s, astronomers made a startling discovery. Instead of slowing down after its fast start, the universe's expansion began to speed up about 6 billion years ago. This surprising turn of events left scientists puzzled and searching for explanations, leading to the idea of mysterious forces like dark energy, or, as some suggest, a misunderstanding of the whole situation. If gravity is supposed to hold everything together, why isn't it slowing down the expansion? That's the big question that has scientists scratching their heads. You'd think gravity would gradually act like brakes on the universe, but instead, we've discovered a mysterious force called dark energy. This invisible energy makes up about 70% of the universe, working against gravity and driving the rapid expansion we're witnessing. The catch? We can't see, touch, or measure dark energy directly. What we have are theories and educated guesses trying to understand this elusive force that influences the fate of everything in the universe. Just when things started getting complicated, the James Webb Space Telescope came along. It revealed ancient galaxies that are surprisingly large for their age, almost like cosmic babies with the weight of adults, which added more mystery to our understanding of expansion. At the center of this confusion is something called the Hubble constant, a number used to measure how fast the universe is expanding. Here's the twist. Different methods of measuring this number keep giving us different results. Webb's observations have added to this baffling mix. The further we look into space, the more questions arise. Is the expansion happening faster than we thought, or have we misinterpreted how space works? Things are getting even trickier. According to what we believe about the universe, the Hubble constant should be around 67 kilometers per second for every megaparsec, a huge distance. But observations, including distant exploding stars and other cosmic phenomena, show a higher number, around 73. This isn't just a small discrepancy, it's a significant mystery in the field of cosmology. To clarify these numbers, scientists are now relying on data from the James Webb Space Telescope. Re-examining data first captured by the venerable Hubble Space Telescope, the Webb Telescope has unveiled a breathtaking view of the cosmos with unparalleled clarity. The findings? An astonishing rate of 72.6 kilometers per second per megaparsec, a figure that sends ripples through the scientific community as reality once again defies theoretical predictions. No matter how experts analyze the numbers, the results overwhelmingly indicate that the universe is expanding at a pace unfathomable by our current models, leaving a sense of mystery hanging in the air. And yet, amidst this cosmic uncertainty, a few brave minds are daring to venture into uncharted territory. One such mind is Lucas Lombriser, a daring theoretical physicist from the University of Geneva, whose bold assertions have dropped like a cosmic bombshell on established ideas. He provocatively posits that the universe may not be expanding at all. In a radical shift from conventional wisdom, detailed in his groundbreaking publication in Classical and Quantum Gravity, Lombriser suggests that what we perceive as the universe's expansion could merely be an elaborate illusion. Rather than racing outward across the cosmos, he proposes that the universe might be flat, static, and utterly motionless. What evidence supports such a jaw-dropping claim? Lombriser and his team go beyond mere speculation. They are meticulously rewriting the laws of physics, fundamentally reformulating our understanding of space, time, and the very fabric of reality. If Lombriser's conclusions hold true, they wouldn't simply resolve the long-standing Hubble discrepancy. They could well dismantle our entire comprehension of the universe. Not only does Lucas Lombriser's theory challenge the widely accepted notion of an expanding universe, but it also flips the entire cosmic narrative on its head. According to him, the striking redshift observed in distant galaxies, the very phenomenon that has been the cornerstone of evidence for universal expansion, can be explained in a radically different manner. Instead of a universe stretching like a balloon, Lombriser proposes that the redshift is the result of changing masses of fundamental particles, such as protons and electrons, over the eons. In essence, it isn't the fabric of space that is expanding, it is the very nature of the particles that are evolving. In this richly woven tapestry of ideas, Lombriser introduces the concept of a cosmic field that envelops all spacetime. This field serves as the crucible where particles arise, exist, and interact. It is this dynamic field, not the expansion of space, that accounts for the redshift phenomenon.
Within this revolutionary framework, the notorious cosmological constant, often viewed as a harbinger of expansion, is recast as a mere reflection of the mass of this cosmic field itself. As this field undergoes fluctuations, so too does the cosmological constant, indicating a monumental shift in our perspective. But that's not where the intrigue ends. Lombriser's model aligns astonishingly well with redshift data, surprising even him with how effectively it addresses the enduring cosmological constant problem. This same paradigm could potentially unravel solutions to two of astronomy's most elusive enigmas: dark matter and dark energy. Historically, dark matter was concocted to address the peculiar rotation speeds of galaxies, speeds that far exceed what would be predicted based solely on visible matter. This unseen mass is thought to outnumber ordinary matter by a staggering ratio of 5-to-1, yet it remains frustratingly elusive. As we stand on the brink of a profound evolution in our understanding of the universe, Lombriser's audacious theories could herald a new era in astrophysics, challenging not just what we know, but daring us to rethink how we perceive the cosmos itself. Lucas Lombriser presents a bold hypothesis suggesting that fluctuations in a proposed cosmic field could mimic the behavior of an axion field. Axions are theoretical particles posited as candidates for dark matter, characterized by their neutral charge and lack of spin. If Lombriser's theory holds, it could radically redefine our understanding of dark matter, positing it not as a distinct entity, but rather as a manifestation of this cosmic field's dynamics. This reimagining implies that the phenomena attributed to dark matter might simply be quirks of a more intricate universal field. Moreover, Lombriser's framework may also bridge the gap to understanding dark energy, the mysterious force driving the universe's accelerated expansion. In this unification, instead of relying on two elusive components, dark matter and dark energy, we might look toward a singular fluctuating field that governs cosmic behavior. Lombriser provocatively posits that the enigmatic force often labeled dark energy may not exist at all. He theorizes that the observed effects traditionally explained by dark energy can instead be accounted for by variations in how particle masses evolved over the cosmos's timeline. The scientific community's response to this radical proposition has been mixed. Luz Angela Garcia, a physicist from Colombia's Universidad ECCI, acknowledges the intriguing nature of Lombriser's theory. Although not directly involved in the research, she recognizes its potential to address several long-standing issues in cosmology, particularly those arising from the discrepancies between observed phenomena and existing models of the universe. However, Garcia emphasizes the need for caution. While Lombriser's model is undoubtedly elegant and theoretically appealing, she points out the significant challenges posed by the inability to test many of its central components with current scientific instruments. The proposed cosmic field and the notion that evolving particle mass could supplant dark energy remain largely theoretical, as we currently lack the technological means to directly verify or falsify these ideas. This leads us to ponder whether Lombriser's ideas signal a retreat to the classical conception of a static and unchanging universe. The answer is nuanced. Despite the excitement surrounding Lombriser's theory, the scientific community is approaching it with the careful skepticism such groundbreaking ideas warrant. Thus, we find ourselves in a state of cosmic uncertainty, balancing between the established model of an expanding universe and the tantalizing possibilities that Lombriser's hypotheses present. So, as we navigate this complex terrain of cosmic inquiry, we invite you to engage further. Remember to press the thumbs up and subscribe button to stay updated with our latest explorations in the mysteries of the universe.